of the Confidential Computing Consortium, and I'll go ahead and turn it over to our panelists.
Thank you. Yeah, I'm Dominic Mulligan. I'm here today to present Veracruz. It's a project that we've been working on internally within ARM Research, which is now adopted by the CCC as a project. So I'm joined today by three other members of ARM Research, Derek Miller, Shell Zhang, and Christopher Haster. They've all been working on Veracruz for quite a while as well. And whilst I'm going to be giving the introductory part of this talk, explaining the motivation and some of the use cases for Veracruz, Derek, Shell, and Chris will be going into some more technical details later in the talk. So to give some background for the Veracruz project, I think it's now an undeniable trend in the semiconductor industry that there's this kind of idea of adding explicit support for confidential compute to hardware. So depending on the particular kind of hardware architecture, these features go by by a lot of different names. So for example, you could have secure enclaves in the case of Intel SGX, realms in the case of ARM's newly announced confidential compute architecture, protected virtual machines for AMD SEV, and so on and so forth. So because there's lots of different names for them, and a few of these names have now become strongly associated with a particular technology, I'm going to use the generic phrase isolate instead of one of these particular names throughout the rest of this talk. So although kind of provisionally very different, there's a lot of generalities that can be said about some of these technologies. For example, they all aim to provide strong confidentiality and integrity guarantees to the software and data that exists within them. And the other thing that's interesting about them is they're also tend to be associated with remote attestation procedures. So these are cryptographic protocols that allow a skeptic to challenge the authenticity of a particular isolate to ensure that the isolate is legitimate. It's actually running on real hardware and it's not being emulated, for instance. And also to measure the contents of the isolate to make sure that the software inside it is what we think it is. So the question that we had when we started the Veracruz project is, if we assume that these technologies have become very widespread, and that, for example, every mobile phone or every server now has access to some isolation technology, what new distributed systems, what new data-intensive applications can be built with them? In designing Veracruz, we tried to go very, very general with this. We didn't build a specific kind of computation or protected privacy-preserving computation. Rather, we tried to provide a framework which can be used to describe and define a wide range of privacy-preserving collaborative computations. And these all use these isolates, these strong isolation technologies that I mentioned on the previous slide, as a neutral ground for computation. So you can take this Veracruz framework, which consists of a number of protocols and tools and runtimes and so on, and specialize it in a way that I'll get to in the next few slides to obtain a particular privacy-preserving computation of interest. Okay. So in the general case, a Veracruz computation consists of n mutually distrusting data providers. Now, each of these data providers is tasked with providing an input to the computation. So they have a private data set that they want to provide to the computation, and they want to, along with the collaborators, kind of apply a function that's provided by a single program provider to those n data sets and produce an output. So that's the general setting for a Veracruz computation. And paired with this idea of these n+1 collaborators, there's the idea of a policy. So the policy describes everybody involved in the computation and describes their roles. So for example, there's the idea of a data provider role and a program provider role, which I've just mentioned, but then there's also the idea of a result receiver. So they're the people or the collaborators that can actually take charge of the result and receive it back from the computation once it's finished. And it might be the case that, for example, a data provider also doubles up as the program provider, or all the data providers in a computation are also the result receivers. So a principal or a collaborator can have a mixture of roles, and all those are specified in the policy. So to give a very, very abstract or pictorial kind of overview of what a Veracruz computation consists of, as I said, we've got these n+1 collaborators consisting of n data providers. Each one of those are contributing a data set, here D1 through Dn as input, and they're paired with a program provider that's providing a function, and that's denoted by pi here. Now, along with them, there's also another principal or collaborator that I haven't previously mentioned, and that's the untrusted host. So the untrusted host possesses a machine that is capable of spawning some instance of a strong isolation technology, so an isolate, so something like Intel SGX or ARM CCA or so on and so forth. So one peculiarity of the Veracruz project is that we support a wide range of isolation technologies. So the isolate could be spawning, in the case of Veracruz, an Intel SGX secure enclave, an ARM trust zone trusted application, an AWS Nitro enclave, or an instance actually of the high assurance SEL4 hypervisor, which is a software isolation mechanism. And so the other three are hardware, whereas SEL4 is software. So each one of these has a different threat and trust profile. Depending on the particular kind of context of the computation, you can mix and match. You can find a technology that kind of suits your particular computation. So once one of these isolates has been spawned by the untrusted host, they go ahead and load the runtime, the Veracruz runtime. So this is open source. I'll provide the repository URL at the end of this talk. And we can assume that everybody has audited this runtime, or they're at least happy that it isn't backdoored by kind of reading through the code. And the way that they check this, they check that the runtime that they have audited is in fact the one that's loaded in the isolate, is by using remote attestation. So every participant, before provisioning any sort of secret into the runtime loaded inside the isolate, will challenge its authenticity using remote attestation. And as previously mentioned, there's also this idea of the policy which parameterizes the computation. So intuitively, you can think of the policy as kind of capturing the topology of the computation, describing who is able to provide inputs, who is able to receive outputs. So by pairing a policy with a program, you can vary the actual computation that Veracruz that is specialized towards. So this policy is very important to understand before anybody takes part in the computation. So we assume that it's public, it's been published by the untrusted host, and there's also facilities in the trusted Veracruz runtime for retrieving a copy of the policy, or at least a hash of it, so that you can make sure that, again, the policy that has been audited by you and that was published as a participant is in fact the one that's in force and is enforced by the runtime. So now everybody involved in the computation has challenged the authenticity of the runtime and the isolate using remote attestation. So they can go ahead and provision their secrets directly into the runtime itself using a TLS link that terminates inside the isolate. So from the point of view of the untrusted host, they can't actually see any secrets that's passing into the isolate itself. The TLS protects it, or also makes sure that the host can't do any sort of can't fiddle with the integrity of the messages passing along that link either. So one of the result receivers then triggers the computation by issuing a message requesting the result, which causes the Veracruz runtime to go ahead and do some computation. And once that's finished, they can all retrieve the result. And again, this is via a secure TLS link, which means that nobody else other than those result receivers is capable of observing the result. Okay, so that's a very abstract overview of Veracruz. So I'm now going to discuss a few specific use cases of how you can take that kind of abstract framework that's parameterized by this program and a policy and apply it to some problems of interest. So here I'm going to discuss secure sensor aggregation. As you can imagine that we've got a context where there's 3 different sensors or multiple different sensors throughout the environment. Some of them are passive, for example, this CCTV camera and this speaker or microphone. They're just sat around, just passively sensing. Whereas some of them are more active, for example, this drone, and it's got a camera and it's flying around and picking up things of interest. Now, each one of these sensors has a local view, so it knows what's going on in its vicinity just by using its sensor. But what we'd like to do is we'd like to aggregate each of these local views into a kind of a larger global view and find out what's going on overall. Now, a specific example of this that's actually been deployed in many cities around the world are gunshot kind of triangulation services, where you have sensors around a city and they're passively trying to work out where, if they hear a gunshot, where exactly that gunshot is, so that the police force for the city can be notified quickly. Now, what you don't want are these sensors that are spread out around the city to act as like a panoptic and like a massive surveillance network that somebody bad could hack into and find out what's going on, or listening on conversations around the city and so on. So one way of kind of shielding this from those malefactors that are trying to surveil a city would be to use Veracruz. And for example, you could imagine a city using an untrusted edge device dotted around the city to do this kind of stitching together of the local views to try and work out or triangulate gunshots. And you want to protect the privacy of that computation going on those untrusted edge devices. So if you imagine the untrusted edge device has Veracruz loaded on it, then each of the sensors is one of the data providers that I mentioned on the previous slide. And the owner or the coordinator of those different devices is the program provider. And they're going to provide the program that takes all of the local views, stitches them together into a global view, and then receives the results. So if you take the description that I provided on the previous slide, you'll see that actually using Veracruz, nobody other than that program provider, the coordinator of all the different devices, is capable of extracting that global view. So we're going to come back to this example a bit later when my colleague Chris talks, because we've got a demo that is in a similar spirit to this. So another use case, another example would be private social graph analytics. So if we imagine we've got 2 mistrusting individuals, Alice and Bob, and they each have a private social graph. And what they want to do is they want to come together and find out whether they have any contacts or friends or enemies in common. But neither of them wants to let on who they actually know, the full extent of their social graph. So again, they could use Veracruz for this. So arbitrarily, we'll assume that one of them, for example, Alice, prepares a program that does the social graph intersection, and she reveals it to Bob, who audits it. So Alice in this situation is both a data provider and a program provider, whereas Bob is only the data provider, and actually both of them will also be listed in the policy as result receivers. So once this program has been audited, Alice is going to provision the program and her data set, and Bob will provision his data set as well into a Veracruz instance. And one of them will trigger the computation, which is protected inside the isolate. And they'll find out that actually, yeah, they have at least one contact in common, Charlie. And as they're both listed as result receivers, they can securely obtain that result from Veracruz, and nobody else other than them will find out that they know Charlie in common. Okay, so we've actually identified many more use cases for Veracruz. For example, we could use Veracruz for private set intersection or privacy preserving machine learning, or even oblivious routing in maps. So for example, if you want to find out how to get from A to B, then you could use Veracruz for this without letting on where exactly you are, what 2 points you're interested in. So there's lots and lots of use cases that we can hammer in to this idea of N+1 collaborators, where we have N input providers and a single program provider and the various result receivers. And it turns out, with a little bit of thought, there's many use cases that we can use Veracruz for. So those two that I just discussed are just two use cases. So that is a very quick motivation and introduction. That's my part over until the very end of this talk, I'm afraid. I'm now going to hand you over to Derek Miller, who is going to talk a little bit more about Veracruz's use of attestation. So as I mentioned, Veracruz supports many different isolation technologies, and we're interested in adding more. And actually this causes some complications with our use of attestation, and Derek's going to provide a bit more detail though. Then Derek's going to hand over to Shell Zhong, who'll talk about the design of the runtime and the programming model that we're using at the moment, and also the one that we're currently switching to, before handing over to Chris Haster, who will talk about embedded clients and using microcontrollers to interface with the Veracruz runtime, and also provide a bit of a demo. And then it'll come back to me to conclude and take questions. So on that note, I'll hand over to Derek. Derek, away you go.
Thanks, Dom. So I'm going to start out with a brief description of attestation. I imagine the audience is fairly familiar with this, so I won't go too deep into it. But at its root, attestation is a way to establish trust in the state of a computing environment. This state can be the software that's currently being run on the system. It can also be used the software that was used during boot, and also the configuration of data of that software or that boot software. One of the challenges with attestation is that there's lots of different protocols, and some of them are more complicated than others. There's Intel EPID, which is probably the first one that most people became familiar with. It's got some very unique protocols in privacy to it. That makes it a bit more complicated as well. TPMs, of course, trusted platform modules, they have an attestation protocol. The platform security architecture's PSA attestation protocol is also one that we support. And then there's also AWS Nitro attestation, which is unique in its own ways. These attestation protocols often rely on an external party to authenticate the signed tokens, or sometimes these tokens are referred to as documents. So with that, I'll start with a canonical attestation protocol where we've got a brand A system and a brand A attestation service and a client, which I have here as a drone because drones are cool. So, and the attestation starts with the client, the drone, issuing a challenge to the system, which gets a token back, and then it has to authenticate it using the attestation service. And only after that attestation is done can the client establish a secure channel to the system. And for Veracruz, we use TLS for this, as Dominic mentioned earlier. So this is fairly straightforward and simple. But now let's say add another attestation service, a brand B attestation service. And we have to do the same steps over again for that, and also communicating with the brand B attestation service and establishing the client. So that means if we want to run the same software on both clients, both of these clients here, both of them have to have, they have to have the software that can do that attestation. They also have to have an existing trust relationship with that attestation, with both attestation services. Sometimes that trust relationship is nothing more than having a public key and certificate for that attestation service that you trust. At other times, you also have to have login information and account information for those attestation services. Doing all of that on a client, especially on a thin client, as Chris will talk about in a little bit, starts to become fairly onerous. So with the problem of multiple attestation services, we decided that the solution was to, of course, to add another one, which we refer to as the proxy attestation service. The flows here are going to look familiar, but the participants are slightly different. So when the brand B device boots, or not the device, but the enclave boots, attestation is initiated from the proxy attestation service with a challenge. It gets the token back and it authenticates it against the brand A attestation service. Same thing goes for the brand B device and the brand B service. The same thing has to happen. Note that now it's the proxy attestation service that has to have the existing trust relationship with the different attestation services. The login credentials. It also has the onus is on the proxy attestation service to be able to support all the different protocols. But now, when it's time for the client to attest, it issues a challenge and gets a response back from the end device, but instead of communicating with the device specific or the brand A's attestation service, it only has to communicate with the proxy attestation service. And from that, we get our TLS connection, and the client is ready to go. Same thing happens for brand B. It's still going through the proxy attestation service. So the clients don't have to worry about supporting multiple protocols, and they have simpler software and simpler trust relationships. Another advantage of this is that the proxy attestation service can be used to enforce policy, as opposed to relying on the end clients to each have the same and coherent policy. That being said, if you look, there's still a lot of back and forths for the client. 6 back and forths at a minimum. Some protocols have more. And we think we can make that simpler. So what we're currently working on is a rearrangement of those trust relationships, not the trust relationships, but a rearrangement of how we do the communications. And so now what we do is we have a certificate with the proxy attestation service, and the proxy attestation service is going to act as a certificate authority, and it's got its proxy private key there. The drone devices, the client devices have existing certificates. They have a trust relationship with the proxy attestation's CA certificate. So when the enclave boots up on the brand A device, it again does attestation with the proxy attestation service and the brand A attestation service. And then at the end of that, it receives a certificate issued by the proxy attestation service. So the proxy attestation service is again acting as the CA or certificate authority. It is issuing a certificate to that device. Same thing happens with the brand B device, and it ends up with its own certificate. Now, when the client wants to connect, it issues a TLS client hello message and a TLS, and then it gets back a TLS server hello message. And in that message, it receives the device's certificate and the proxy attestation certificate, and it can then authenticate it. It's one back and forth for the client before it's got a secure session established. And the same thing happens for the other. So at this point, the client has to use what just basic, mostly basic TLS client software on it. No special attestation services. And you notice that the communication is much better. This is beneficial for low-end embedded devices that maybe are battery constrained, memory constrained, or also on extremely low bandwidth protocols such as LoRa, WASM, or even BLE. You can imagine situations where that can be helpful. So the issue of policy enforcement sort of brings up a different question. So how do we allow the client to select a platform profile? For example, the client only trusts SGX systems, or the client only trusts Nitro systems. In that situation, then and I'm still working on the code for this right now. So and you guys are keeping me from my work, by the way. So anyway, so the proxy attestation service can select from a list of certificate key pairs to sign with based on the profile of the platform being attested. For example, brand A attests, and the proxy attestation service can select a certificate specific to brand A or brand B, or we can get even more interesting where we have a tree of certificates. So instead of saying, I only trust SGX or I only trust TrustZone, you can say, I only trust systems that have encrypted DRAM, for whatever your level of paranoia is. Or you can also select, I only select TrustZone systems that have encrypted DRAM, or ACA systems. And so basically, if with a tree of certificates, the proxy service can then select the proper profile certificate to sign with, and then the client, a priori, before this communication happens, has already selected the certificate that it trusts. So at that point, the client then will reject certificates that are signed with a profile that it doesn't, that are outside of its scope. But it will accept a number of certificates. For example, anything, if it selects target profile ACERT on the left, then any of the AA, AB, or AC profiles will also be authenticated for it. So it's it's a fairly straightforward policy enforcement. It's basically selecting which certificate or certificates the client trusts. And with that, I will hand off to my colleague, Shale. Thank you.
Okay, cool. Hello, I'm Shell. In this section, I will switch gear to focus more on the Veracruz runtime. Particularly, there's an ongoing rework on the runtime and why we want to do that. So let's first talk about our existing runtimes. So the existing runtimes are single-use. The biggest disadvantage here is the WASM program is load and execute by the Veracruz runtime once and once only. This causes some, well, problem. Particularly this runtime, once they reach initialization, they will receive the incoming package from the clients. This including data package from D1 to DN, and also the WASM program package with the pi. Once the runtime receive all the package, they will change the phase to execution phase. They will execute the program and return the result. And at this stage, the result retriever can read the result. And after that, the runtime will be tailed down and including all the program and data inside runtime. Originally, we made this choice with the mind that a tight state machine can provide stronger security guarantee. In fact, we have a strict state machine to control those different steps. Together with the runtime, we designed a buffer-based storage system. To store all the incoming data, the runtime maintains several different buffers on the different indexes. Since it's a single-use runtime, we never store the program. We only store the incoming data. That means we need basically we need to write more code to some degree to process the different type of package, namely the program package and the data package. This can be disadvantages since people need to trust the runtime. More code could be means people need to spend more time to build the trust on the Veracruz runtime. Another disadvantage, which is something we somewhat dislikes, is to allow the program to interact with the runtime, particularly with the buffer, we designed some simple API. You can see we show two examples. One is read input under the buffer under index. Another one is write back to output. Despite those API are fairly simple, but still it's slightly unfamiliar to general programmers. They might misinterpret it, for example, what is the meaning of the index. This leads to a short summary. We identified few limitations for the existing runtimes. First of all, there's slightly a usability problem. As I mentioned before, the program provider must work with the unfamiliar API. The second problem, which is setup costs. Veracruz runtime setup costs could be high. We had a measurement a few months ago. It is a logistic regression algorithm on 700-ish KB data. The Veracruz initialization could contribute 20 to 30% of the overall time, depending on different backend. Of course, this was a not complicated program, nor a large data set, but in the ideal world, we want to reduce the the setup costs, especially in the case if a group of clients want to do multiple tasks. The third, which is also the most important part, we want to support streaming. Obviously, in our single-use runtime, this is, pretty much impossible. Particularly, for example, in the case Dominic mentioned, the secure sensor aggregation, one can imagine different sensor will constantly send a new package to the Veracruz instance, and Veracruz instance will repeatedly call the aggregation algorithm on the incoming data. This is something we really want to support. Given these three limitations, we had a new proposal. The bigger change is we replaced the storage system by a virtual file system. Basically, this virtual file system will manage the incoming data or the programs and also the results. And on top of the virtual file system, we provide or we implement the WASI standard, a WebAssembly System Interface. WASI is a new proposal or standard in WebAssembly. They basically standardize some operating system related API. For example, there are file system related API. There are also some API related to socket, time, and random number, etc. In the first draft, we will focus on, we will implement per se the file system API, for example, path open, read and write, while we choose to ignore those API related to socket and time for now. This immediately brings us some benefits. First of all, improve the usability of the client. Previously, when client provisioning their data and program, they basically send a request under, for example, you can imagine we have a request called program. We also have a request called data. This can be a little bit unintuitive. While with the virtual file system replacement, we can provide requests like read, write, append file, which are way more intuitive. Second big improvement, which is also we want to solve it a long time ago, is we massively improve the usability for the program. So the program no longer need dealing with our custom API. They just need to use standard file system API, and they just compile their program to the WASI backend. At least in Rust, there is a good WASI support. You just need to compile with the WebAssembly 32 and WASI backend. In C, there is the encryption also support compiling to WASI backend. We expected there will be more language to support compiling to WASI backend. So this is good for the Faas. A third benefit is now we can reuse the same runtime. Notice that in the virtual file system, there's no limitation how many programs can be stored. So this means a group of clients, you can imagine, they can use the same runtime to achieve several different tasks. What they need to do is they simply provision it to several different programs. There are two interesting observations here. First of all, given this virtual file system replacement, it is possible to pipe the output of a program as an input to another program. Obviously, in the streaming case, this program are very likely to be the same. However, this also leads to an interesting question. Is there an interesting example or application the program can be different? Potentially a program, it could be two confidential parties. They don't want to reveal their program, but for somehow they want to collaborate together. We haven't identified a very promising case here. However, we will support this feature as observation one. The second observation, which unlikely we will support, is do we want to allow the program directly call another program? Our first instinct is this will have a big impact on the security aspect, so we probably will not implement this feature for now. Given all those changes I mentioned before about the virtual file system, this leads to our bigger goals. We now have a reusable runtime. This means Veracruz runtimes now becomes a service instead of a process that are strictly controlled by a state machine. This obviously fits our big goal to working towards streaming. To some degree, we believe we already have a minimum call. Just to the side note, we already have a draft about everything I have mentioned. We're currently in the test phase to test everything are correct as which we expected. Hopefully, this draft will merge into main soon. However, there are some questions probably we need to answer. Do we want to provide some sort of high-level streaming API? For example, do we want to support some streaming model, push or pull? We don't have a solid answer now. Also, slightly more detail, do we want to implement those WASI API related to socket? We also don't have a solid answer now. We are, at this stage, we are we're also currently actively exploring examples. Maybe those examples can help us to identify what we are missing, or how the streaming can be how all the change can be fit into the streaming computation. This leads to the end of my section. I will hand into my colleague Chris. He will talk about the embedded clients.
Had to unmute, but thanks, Shale. Yeah, so quick note on the term microcontroller scale on the slide. When we're talking about embedded systems actually encompasses quite a wide range of devices, all the way down from small PIC chips that have fixed logic, and all the way up to sort of Linux-enabled devices like the Raspberry Pi that you can run Linux and has an MMU and all of that good stuff. And it's not that we don't care about the upper end of devices, it's just that the existing Veracruz client works perfectly fine in that space. So for this branch of work, we're actually focusing on sort of the microcontroller scale devices. These are smaller. They generally, the main value of these devices is low power and low cost. And it's quite just a bit of a different world from what you get in Linux. So the value of these devices is low power, low cost. The downside, the trade-off there that you make when you get into this space is that you lose the ability to really do as much compute. The more compute you do, the more power it takes. But that doesn't stop developers from wanting to push what applications are capable of. So what we kind of expect to see is more creative workarounds for this compute power cost trade-off, mostly by moving compute off the device and into the cloud or into edge devices for low latency applications. But this comes with a risk, because when we move compute off the device, you now have a lot more fingers touching the data. And so it's no longer self-constrained in the device by the limitations of the physics of the device. So now you have to worry about that. And this is really where Veracruz can become really useful for these sort of applications, by allowing you to move compute off the device without sacrificing the privacy or integrity of the data. So to jump into the example, this is something that Dom mentioned earlier. This is just a very specific example that it's quite interesting, which is audio event triangulation. So this is sort of the example that Dom mentioned earlier of listening. You have this bunch of devices out in the field, cheap devices, battery powered, makes it easy to deploy. Maybe it's a volunteer program that are listening for things like gunshots. And upon hearing an audio event, they can triangulate and report the rough location of the signal. It's quite an interesting use case because audio is a rather rich analog signal that even if you try to obfuscate or blur or remove a lot of the details from, you still risk leaking data from a lot of people in the city. Something else that was interesting that kind of fell out of this demo as we were working on it is we actually also hide the location of the devices from the person who gets the final result. So if it's a volunteer program, you can actually contribute your sensor and contribute the audio stream without giving away the location of where your device actually is. So just kind of a interesting, useful applications. So let's go ahead and jump into the demo we have here. Yeah, so okay. So we wanted to put together a client that would work on these small devices. You can see it, so I'll just go over what everything's here. At the bottom, you can see this is the actual code base for the project. It's all on GitHub if you want to check it out. It's running inside Zephyr, which is an IoT OS. At the top, we have the log for the Veracruz server and the proxy attestation server. I should note that this is using the proxy attestation server work, so it's not using the certificate-based proxy attestation. This is just because of the work has been happening in parallel with what Derek's been working on. So that's some of the future work actually is to adopt Derek's work, adopt the certificate attestation, which I'm actually looking forward to because it means we can simplify the quite a bit and reduce the code size. And in the middle is just another server that's running that is connecting to the Veracruz instance and checking to see if it has reported any audio findings. So let's go ahead and run the demo. This is running in Zephyr, so you could imagine it running on a Cortex-M device. Just simulating it locally for now. First thing I'm actually going to do is I'm going to showcase the policy file. This is the kind of the topology map that Dominic described earlier. It's just a simple JSON file that is compiled into the program. It has a bunch of public keys that identify the devices that are contributing to the computation, and also the entity that's getting the results. It also has the descriptions of the files and the permissions that each identity has separate. Each identity has separate permissions. That's the stuff that Shale has been working on. And we also have, the necessary information to verify the enclave and attest the enclave correctly. So I'm going to go ahead and compile the program. And something else to note is I've added a delay in here just to have some time to explain what's going on. So of course, all building with Zephyr. And we can run it. And so yeah, so we're booting Zephyr, and we're now listening to an audio device. Now the devices can still do some compute. They're not, they have some compute. So you can imagine something like a low pass filter and sort of peak detection to actually grab an audio sample. And then once we have an audio sample, we can take kind of a window, package that up nicely, and sit it in. So here we've got an audio signal. We also likely have GPS, so we have an accurate location of the device as well as a timestamp to discern between different audio snapshots. The next thing we need to do is package it up and send it to Veracruz, but we can't do that until we've attested that the Veracruz instance we're talking to is who he says he is, or who they say they are. So here we've just attested the device. We've sent a challenge, which was at the top, the hash at the top. We've sent a challenge to Veracruz. It's sent back a response, and then we've sent that to the proxy attestation server. Proxy attestation server communicates with the other attestation, with the actual attestation servers, and gives us the enclave hash and the enclave cert hash. The enclave hash tells us that this is trusted. The enclave cert hash acts as the root of a certificate chain, which we can then establish a TLS session with, which is what just happened here. The posts that you see there, the sort of the 6 back and forths, that's the TLS handshake. We're actually establishing it, the TLS handshake, with the enclave that's in the host that's providing the computation. So the host, as Dominic mentioned earlier, the host isn't privy to the data. We've established a TLS session through the host into the enclave. And so here, we now can actually send over our audio sample, which we've just sent with an additional post message. This is, of course, through the SSL, the session, so it doesn't, so the host isn't able to see the data. And then, so that was one case. We've now successfully transmitted our audio sample. But of course, you can't triangulate with just one, so we have to send in, multiple devices have to report audio. So I have 2 more, which I've removed the delay from. You can see one just flew by. It has a different location, a different audio sample that it's detected, and we'll have to send a 3rd one. But after sending these, the compute can now be performed. So once the triangulation service has checked, it will now report the new triangulated location that it found from the audio samples. And so, yeah, so now that that's the computation. We've now triangulated data using the audio samples from these these sort of devices in the field. And again, the audio sample went into the enclave, the location of each device went into the enclave, but they don't leave the enclave. So even though the police force or whoever is at the end can get the location, they don't have access to, none of the untrusted parties in the computation have access to the location or the audio from the devices. So that was it for the demo. Again, the code's all on GitHub. If anyone's interested in checking it out, it's compatible with Zephyr if they want to embed that in their own microcontroller program. And then I will, but yeah, there's questions, we'll have them at the end. I'll hand it off to Dom to reach the end.
Thanks, Chris. Yeah, so I'm going to quickly conclude the webinar now. So we've discussed a few different things, a few different technical aspects in this this webinar, but we're also working on various other things as well that I'll briefly mention. So one of them is looking into how we actually deploy the Veracruz runtime inside a container. So we're looking at integration with Kubernetes. some of you who are familiar with functions as a service frameworks will note that actually Veracruz has a lot of similarities with like the function as a service paradigm. However, it's a bit more general than the typical function as a service framework in that we allow multiple different participants to supply inputs. What we're doing at the moment is looking at how we can kind of constrain the Veracruz design to fit into one of these existing frameworks, open Faas, and deploy it as part of a function as a service kind of deployment. We're also looking at adding support for additional isolation technologies. So as a first step to that, we're actually porting Veracruz to the runtime to run as an unsecure, or like just as a plain Linux process. So this is a first step in being able to support technologies like AMD SEV and similar. So the other thing that we're doing is looking at spinning out a reusable hardware / attestation abstraction layer. So we've put a lot of work into supporting various different technologies, both in the actual kind of isolation layer and also how we attest them, as Derek highlighted. And it really makes no sense for various other projects that might want to do something like this to reinvent the wheel. So what we're trying to do is spin this out into a library that can be reused. So in future work, I'll just mention two ideas that we've been discussing within the project. One is bounding the behavior of the program binary. So at the moment, the binary that is supplied by the program provider is either completely opaque or completely transparent, in the fact that the program provider might declassify the binary as a kind of a first step in trying to persuade somebody else to take part in a collaborative computation. However, we can think of a middle ground where, for example, the binary remains completely opaque, but the program provider chooses to declassify some properties that the binary might have at runtime, in which case the runtime itself, the trusted runtime, would enforce these properties and make sure that although nobody can actually see the program that is being executed on the input data, it's known to satisfy these various properties, which would be captured in the global policy. So that's one thing that we're looking at. It would be a middle ground, a kind of semi-declassification of the binary. So another interesting use case, or family of use cases, I suppose, would be looking at larger multi-enclave examples of where we could use Veracruz. So this would be taking things like Chris has just demonstrated, where you have multiple kind of computational elements, or even multiple Veracruz enclaves, so runtimes working together to solve some problem. So here, because we support many different isolation technologies, lots of interesting research challenges. So for example, for a typical distributed computation, you can imagine that there's parts that are very sensitive, and there's parts that are less sensitive, and therefore in terms of privacy, and therefore it makes sense to try and schedule them onto different isolation technologies supported by Veracruz. And how we go about describing that sort of thing and actually mapping them is an area of open research that we intend to look into. So as I mentioned at the beginning of the talk, Veracruz is now adopted by the CCC as a full project, a full confidential compute consortium project. Our intention in joining the consortium was to try and attract collaborators and try and attract contributors to the project. So I'm pleased to say, since we joined the CCC, we are now engaged in at least one collaboration with another CCC member called IoTex. And we're looking into using Veracruz as the substrate for doing some privacy preserving image processing from an IoT camera that IoTex produce as a product. So that's been very fruitful. And it's actually driving a lot of kind of innovation within the project right now. But of course, we're interested in many more collaborators and contributors, and we're also interested in people bringing their own ideas to the project and pushing it in various directions that we didn't think of. So the Veracruz repository is there. Please do take a look, contribute if you like. We now have a Slack channel under the CCC's workspace, and also we host public Zoom meetings every Thursday. All the details are in our repository's README of how you get in there. as it says on the slide, we've got a lot of issues that are suitable for newcomers, self-contained and relatively simple in our issue tracker, along with ones that are more ambitious if that's what you're after as well. So that's about the end of the talk. I'll just make some closing remarks now. So Veracruz is basically an exploration of what the strong isolation technologies like ARM, CCA, and Intel SGX are capable of. So in particular, we're trying to work out how, taking these as a primitive, we can design new data-intensive distributed systems built around them. And in Veracruz, we've focused on building a very general system, one that can be parameterized by a program and a policy to obtain concrete computations of interest. So the use cases of Veracruz are very similar to cryptographic techniques like secure multi-party computations and homomorphic encryption. If you're familiar with those, you'll probably recognize that actually things like private set intersection and so on that I mentioned earlier are typically addressed using pure cryptography. However, we'd argue that Veracruz is much easier to understand than these advanced cryptographic techniques, arguably easier to use and also easier to deploy, as hopefully this webinar has convinced you of. So that's the end of the talk, and we've now got some time for questions if there are any. I see that there are. Stefano, are you taking the questions, or should we do it?
I guess I'll jump in. I'll answer the. There's a number of questions that are about attestation. Ben Fisher asked the question, why did we create an attestation service versus relying on TPMs and attestation from something like Keylime? First answer is, I'm not familiar with Keylime. The other answer is that we started with SGX, and I'm not aware of how a TPM would have visibility into the state of an SGX enclave in order to perform the attestation. So where we started was with SGX's EPID attestation, and then we moved forward from there. So I'm going to need to look into Keylime, see if there's anything we can do that. The other issue I would say is that TPMs are not universally available on all the platforms that we might like to support. That being said, since I don't know much about Keylime, that's something that I need to read about. So thanks for that. Thanks for that tip. So Mohammed Sardar had a question about having dealt with various remote attestation mechanisms with different threat trust models. Couldn't I share some insights? For example, what were the challenges? I would say that the challenges, I would say, starting with SGX EPID, is the challenges is that the interface is not the interface, but the protocol itself is fairly opaque. It's a unique protocol with multiple passes because it has unique properties. The challenge that I experienced is that there's not a lot of good documentation on exactly what needs to be done in each step. There is example code, but the example code doesn't always tell me why I'm doing the things that I need to do, and if there's different aspects of things that I'd like to do. So that was the challenge that I had with EPID. We've worked through it, and I do understand it, but it was a bit of a steep climb. For ARM PSA attestation, I did have the challenge that I had on that was that there just weren't there's one implementation available and was written in C. We are a Rust-based project, so we had to do some interfacing on that. It also we had to do some change the meanings of some of the fields in the tokens. Now, AWS Nitro is a really interesting question because one thing, they don't have an attestation service. They have a long-term key and certificate that they use to sign their I think they refer to them as documents. That means that there's no external attestation service to check against. So the client could check the attestation themselves just using that key and certificate. That's not what we do because we still have the support on these other platforms, but we could do that. The other thing about AWS Nitro is that the trust model on Nitro is quite a bit different than it is with SGX or AMD SEV. Since AWS Nitro is providing you AWS is providing you your document and signing your document inside one of their services, as opposed to Intel, well, let's say Intel running on a different cloud service provider where you've got two parties, the cloud service provider and Intel, that would need to collude to compromise your data. With AWS, it's one entity. That being said, AWS has a lot of safeguards around this, and I'm not throwing shade on AWS at all. But the purpose of AWS Nitros is not necessarily to protect your data from AWS. It is more interesting, for example, if I am a user of a service that's running on AWS, let's say I'm using Signal Instant Messenger and it's running on AWS. Signal can assure their users that Signal itself can't see your data by putting it inside an AWS Nitro enclave. So the relationships and the trust relationships on Nitro enclaves it's a very different thing. If you don't trust AWS with your data, you're not likely to trust AWS Nitro enclaves. But if you don't trust a service provider like Instagram or whoever might be AWS's customer, you don't necessarily trust them with your data. Nitro is very appealing for that purpose. It's also, I have to say, quite a bit less restricted than the other environments that we've worked in. I haven't worked with AMD SEV though, so I suspect it's going to be fairly similar to that. And Mohammed also asked, what protocol do we use for the provisioning of the proxy key? Right now, it's just a priori defined. We haven't worked through that problem yet. So if you have ideas or opinions on that, please submit, talk to us on GitHub or in any of the forums that we have available, because that's not really an answered question that we have. I think, yeah, another question. This is for Dominic, I think.
Yeah, so I think the first part of this question is about the bounds that the CCC themselves put around to kind of what's in scope for confidential compute. So on that, I would say I think the CCC are entitled to try and limit what is eligible for membership of the CCC, and hardware kind of based approaches seems as good a kind of bound as any. So on our use of SEL4, so the reason why this came about is because we have another project within that originated within ARM research that's now open source as well, built on SEL4 called IceCap. And really this is why the SEL4 integration came around. So yeah, Veracruz does support both hardware and software. And yeah, basically we just saw some low-hanging fruit to integrate two of our projects, and we went ahead and did it. So that's the motivation there. So are there any, I'll take the next one as well. Are there any formal verification efforts going on for Veracruz? Not currently. So in the past, we did have some formal verification of the runtime itself. So in the past, we had a CBMC, so the C-bounding model checker flow for verifying various parts of the runtime back when it was written in C. So in particular, we had a custom bytecode rather than WebAssembly at one point, and we had a whole verification kind of framework built around that to verify that this bytecode was doing what it is claiming to be doing. However, we have since moved to supporting just standard WebAssembly runtimes like WASM and also WASM time, and we have no formal verification at the moment, nor do we have any with the protocols that we use in the provisioning process. But if you are interested in looking into this, we'd be very interested as well, because a lot of us do have a lot of sympathy for formal approaches within the project. So I can also handle Nikolai's question. Do you plan integration with the confidential computing architecture announced in ARM9? Yes, we do. I'm not sure how much I can say at the moment about timescales, other than just to acknowledge that yes, we are working closely with the kind of the product group who are developing the CTA, and at some point in the near future, hopefully, supporting Veracruz will land for that product. And I think from what I know, there will be further details announced on the CCA later in the year. So yeah, that's when you'll learn more about exactly what that consists of. Okay.
I will probably take the next question. Yeah, he has actually have two questions. One is the performance number. We do have some performance number in Veracruz against some homomorphic encryption, particularly, for example, against the Microsoft CL library, but it's slightly older version. They probably improve a lot. So the performance number shows, well, it's very old number, Veracruz could be like around 100 times faster in our sort of performance measurement. But bear into mind, it's a very loose number, I would argue, and it's not like those systematic evaluation, those themes. Also, since then, Veracruz has changed a lot. We probably would like to do it again, given we have a drastic change. In terms of our old number, I could try to put the number somewhere, probably in the repository. So, but bear into mind, it is a very loose comparison, just for people who are interested in terms of the performance.
Okay, I think the last questions we have are from Thomas. The question about the freshness of attestation. What happens if the client discovers that the attestation certificate is not fresh anymore? As it is right now in the prototype that I'm writing up, is that the client will reject it because it is expired. What I would like to do is have the compute enclave, the Veracruz enclave, notice when a certificate expires and then request another one. There's a few challenges on that, because inside enclaves, it's difficult to get a trusted time source. Not all enclaves provide that. There's obviously not all enclave technology provides that. That being said, there are ways around that. You could always use something like runtime to an external service. That becomes then part of your root of trust for that. But there's a number of solutions we can do on that. The other challenge is that, like, for example, an extremely thin client like Chris was demonstrating, those clients don't necessarily have a reliable time, clock as well. So that's not a fully answered question on that, but it's something that we're thinking about. And Thomas also had the question about the generation of the attestation certificate. Do you tunnel the attestation report in a CSR to the proxy CA, or are you using some other kind of protocol? What we are doing is, when we send the token, the attestation report, to the proxy service, we have a hash of the CSR in that token, and then the CSR comes alongside of it. This is not a security concern from a confidentiality concern, because the CSR doesn't contain any private information. It has authenticity concerns, which is why we place it inside the token. So it's basically coming along alongside the attestation protocol. In an ideal world, I could just put the CSR in the token, but not all tokens have enough space for that. SGX, for example, I think it limits you to 32 user-defined bytes, and so you end up having to do a hash and then send the data alongside. It's a little annoying because of the way we're using protocol buffers, but it does work.
I can tackle Mohammed's question. What, in your opinion, is the unique feature / use case of Veracruz in its existing form, which is not offered by any other existing frameworks? So I think one peculiarity of Veracruz, at least compared to many other similar projects that we've looked at, is that Veracruz does support many different isolation mechanisms, both hardware and software. So there is another similar project called Baidu Mesa T, and I think it's now been adopted by the Apache Foundation. I think it's now Apache something that I can't remember, but they are similar in that they do support multiple isolation technologies as well, and also they use they also try to address the same sorts of use cases that we do, this idea of secure multi-party computations and distributed privacy-preserving computations. However, we use WebAssembly, whereas the last time we looked at Baidu Mesa T, they were using Python. So this WebAssembly support means that you can write these computations that we've been talking about in many different high-level programming languages. So a lot of the examples that we've been discussing today have been written in Rust, but we've also got a member of the team that's looking into providing some examples written in C and C++ as well. So I would say that that is one kind of peculiarity, at least, of Veracruz in its current form. But I am aware that there are multiple projects working in this space. It's a hot space, and it seems that a lot of people have had similar ideas in the kind of the same time period that we have. So it might be that there is a project similar to Veracruz in that respect. Okay, I think that was the last question, if there's no more. No, I think that's it.
Great. Well, thank you very much for presenting. We're happy to have you here. And thanks everyone for joining. Video will be available shortly on the CCC website, and tune back in for more details.
Great. Thank you.
Thank you, Ashley.
Great, thank you.
Thank you.
Bye, everyone.
Bye.